Yeah, so consensus proofs for better staking pools. Kind of two pieces here. What do I mean by consensus proof? And then how does it support better staking pools? By the end of this talk, you should understand both of those parts, I hope. So as you all know, Ethereum's moved to proof of stake. And there was this huge event of the merge that has gone pretty well. And a key thing here is that there's like two layers to the merge. There's like the execution layer and the consensus layer. And as part of the way this was designed, it was really straightforward to kind of keep these two layers separate. So we had this like execution layer that has been like existing for like quite some time now. Ethereum's birthday is actually coming up. But that's been going for a while. And then in parallel, we made this other chain, the beacon chain. And then the merge was actually bringing them together. But there's still some artifacts of like having these two different layers. And so that leads to some downsides. A big one here being communication between the layers. So what you can do is you can deposit your ETH from the execution layer. When you like go to like get ETH on an exchange, you withdraw to some wallet you have, even say like MetaMask. This is like ETH in this execution layer. When you use all these dApps, that's what we're talking about. If you want to become a staker in Ethereum, you deposit from the execution layer into the consensus layer. So there's sort of this one-way communication there for just ETH, this token that we know. After Chapella, you can now withdraw ETH back, and we saw a bunch of considerations in the last talk around withdrawals and how that kind of works. But the thing is that this is just ETH, right? So there's no way to like communicate more about state between the two layers, at least like trustlessly. And it turns out that there's all sorts of applications. Hopefully some of you in this room will like come up with like new crazy ones that no one thought of before. Around using the state to like do things like, for example, improve how we build staking pools. And yeah, so a big sort of piece here is that there's no way to, again, trustlessly get from the CL back into the EL. Where we would imagine writing smart contracts, applications, things that use this stuff to, again, drive towards more decentralized applications. And there's all sorts of stuff we can imagine. Like there's three I'll call out. There's like a few others I've been kind of toying with. And either way, again, I think there's like a lot that will just not be possible. And it'll be really exciting to see what people do with it. One of them, like staking pools, as everyone talks about, like liquid staking tokens. Another is restaking with things like EigenLayer, which you've probably heard of. There's like probably some applications around MEV management. And I'll get into that later in the talk. But that being said, all these applications we can imagine happening in the execution layer. So, again, series of smart contracts to do different cool things. But without a way to communicate between one to the other, the CL to the EL, you have to have some sort of trusted oracle in the mix to make this happen. Like if you need to know about some update to some validator, say like their effective balance changed. There's no way to know that right now without trusting some other operator to like bring that into the chain. And like commonly these things are implemented via essentially multi-sigs or like things with even like worse security properties. So that's not nice. And that was the point of this EIP, was to essentially actually just remove this trust assumption entirely. EIP 4788. This is included in the next upcoming hard fork, Cancun. And yeah, this was an EIP written by myself, and then with some collaboration with Ansgar and Danny at DF and many others. Yeah, so what does the EIP do? Well, it solves this problem I was just painting for you. It, in a way that we'll see, moves the beacon block root from the consensus layer into the EVM, where it can be used for all these different applications. So let's look at the design a bit. Again, there's nice pieces we can kind of use to understand this change. The first one is this beacon block root, and the other one would be in the EVM. So let's just break that down. So with the beacon block root, what does this mean? So when we say roots in the consensus layer, we're talking about these cryptographic accumulators that we can make proofs against. And what is a cryptographic accumulator? It's this thing where you have these security properties that let you, make proofs about the thing. It's a way to have a very succinct object, a commitment, to maybe a bunch of data. And you'd also like a way to make easily verifiable proofs against the accumulator. And in this case, what we want to is get to the state on the consensus layer. So again, there's going to be some like very succinct thing, some like very small thing that we can take from the CL, put it into the EL, and then we can sometime later have like these proofs, so almost indirectly then verify, hey, I made a claim that at this point in the past, the validator looked like this, and I can actually then provide a proof that that was the case. In particular, the way this is structured is there's this whole scheme called simple serialization that the way you can write everything within the consensus layer is also sort of has this like Merkle tree attached. I'll just assume you know what those are. I'm familiar. Point is that it's again this like cryptographic construction where you can actually say, okay, I commit to some data and later I can prove what that data was. So this is essentially an example. I'll just kind of walk through this. So in this case, we have these accumulators, these roots, and the way to think about them is just 32 bytes. And they have this property that you can almost think of these as like expansions. And now I didn't really draw this out, but the way to think about this is like each layer here is like sort of some part of some tree. Like the idea is this would be at the very top of some very big tree, which is like pointing to the beacon state. The beacon state is this like very big thing, and then like there's a subtree, which is the validator. And the idea here is we want to say, okay, I have the root at like some slots, and I ultimately want to know, was this validator slashed? So you could say, okay, here's the root. In particular, with this EIP, we work with block roots. So you have the block root, that commits to the block, and here I just show the header of this block. That commits to, say, the state, which then commits to the state object, or sorry, I guess I'll say it commits to the state root, which commits to the state object, which has a list of validators. You can pick the validator you want, get down into it, and eventually prove, for example, in this case, just this one byte, slashed or not. So that's kind of the idea. So we have all this like cryptography, which is pretty cool, so we can like prove arbitrary things. And this is like, again, this is only a partial view of the state. There's a bunch of cool stuff in here. Essentially, anything we care about at the consensus layer is committed to in some way via some data structure in this state. So it really does open up like a hopefully very like large design space for all sorts of things that we could care about, including staking pools. So now there's a question of, okay, we have this like beacon block root, and it lets us like, prove things about the state, and that's pretty cool. But how do we go from actually getting it, where they sort of exist, let's say on the CL, into the EVM? And that's the next part of this EIP. So the way we're going to do that is essentially use this thing called the engine API. And I'll just keep it kind of high level, but basically, again, reflecting this sort of dual layer design of the merge. There's a consensus client and an execution client. If you like run nodes, you might have heard of like Geth, Lighthouse, Prism, Besu. There are others. Point is, there are many client implementations for each layer. There's also validator clients attached with the consensus client. So when you actually go to run the software, this is the thing that's holding your staking keys. This is the thing that's like managing the beacon state and like reorgs on the beacon chain and all of this. And then this would be the thing, verifying the execution, whatever's in the block. The important bit here is that there's these APIs that connect all these pieces. And they're here because the idea is, again, you could have different implementations of the consensus client interact with different implementations of the execution client, and they should all work together. For this EIP in particular, what you're going to do is pass the beacon route along the engine API. So again, it's like, in some sense, it like lives here. You're just going to pass it along. The way this kind of works is that for every block that the consensus client gets, it's going to check the validity of the execution payload, the execution part of the block, by passing it across this engine API. And under this EIP, we just also then pass the block route. So that's what it says here. You have the CL. For every execution block, you're going to pass along also the parent beacon block route. That part's important because if you passed along the block route, you'd have the circular dependency. It would basically get to a point where I use the root in some smart contract, which is going to change the execution of the block, which is then going to change the root of the thing, which changes the thing that goes into the EVM, and hopefully you can see there's a cycle. So it's in the parent beacon block route, so there's sort of this latency of one slot, but not really a big deal. So we're going to send the parent block root across the engine API that goes into the execution payload header. This is important because it supports syncing. I think I'll say a bit more about this in a second. Yeah, I'll get to that in a second. And yeah, then basically what after that is with the root in the header, you then write it into the VM as this thing called a stateful precompile, which is also a kind of new concept the CIP introduces. And we'll look at that in a bit. So some questions that immediately come up is like, why the parent beacon block root? Well, it's kind of what I said. You have this circular dependency. If you try to use like the block root of, it just doesn't make sense. There's a syncing question. So again, this is like an architectural decision of the merge. You kind of want the EL and CL to be as independent as possible. And so what that looks like is like the CL could say, hey, here's like the tip of some chain. It could then turn around the next slot and say, here's the tip of some other chain. And the EL may not know about this. So then it needs to run off and like sync this other sort of fork of the chain. And it's nice to just have these be as uncoupled as possible. If they kind of worked in lockstep synchronously, yeah, it wouldn't be as nice. Just take my word for it. And so because of that, what that means is that if the EL is like off syncing some chain, then it needs this information, for example, the parent beacon block root, without talking to the CL necessarily. So that's why we put it into the header. And yeah, then you just go along and get to the head of whatever chain over here is. So I mentioned the stateful precompile. This is actually pretty new. So inside Ethereum, we have this concept of precompiles. And the basic idea is there's some things we want to do in the EVM that are just too expensive to write as like smart contracts, as like EVM bytecode. So instead, we can say, OK, for some things we all agree to, for example, like SHA-256, the hash function, we can like point to the way to think about it as like a native implementation that just exists at like some special place on chain, and we can all use that. So similarly, we wanted to do this with the CIP. And in particular, there's now this new concept for the precompiles that they're stateful. For example, with like SHA-256, that's just like a hash function. You give it some bytes, it gives you back the hash. There's no like state it needs to maintain. Well, now we want to actually have like a history of these roots. And so now there's this state that needs to be maintained within this contract. Again, for like you as the end user, you probably don't really care about this, but it actually has interesting security implications, so it's worth calling out. The reason why is because this actually supports stateless clients. So if we move to, say, vertical tries or something like this, then we get to a place where you don't want, or I'll say this instead, like how an analogous feature works today with the block hash of the execution layer is that you don't write them into the state. They're just in this like history buffer. There's just like an ambient history of like the last 256 hashes. And what that means is that if you were to make the protocol today stateless, you would basically need to like have the state and like this other little thing, which is just like kind of annoying. So this is actually much cleaner. If we have one very self-contained thing, it makes it easier to make proofs and generally supports, again, a move to stateless clients. So we have these concepts. We're passing the root along. What are we going to do? So like concretely, before you even execute any transactions, you're going to take the root, you're going to write it into the stateful precompile, which again is just like some address. There's some state, just like any other account on Ethereum. You write it in there. Now the idea is that any transaction in that block can call into the same precompile, say with the timestamp that it is interested in, and get back the root. And there we go. We have trustless access to the consensus state, and that's what we wanted. We can now verify proofs, make all sorts of claims about the CL. That's pretty cool. So what I kind of described so far is like almost a design where every block you're sending the root over. And what that means is that with each new block, you could imagine just overwriting what was there before. You could do it this way, but the issue is that you would then need to be like, you'd essentially need like the next same slot inclusion to use this thing, like at all. Because you would like write this, you would write like the parent root, you would like say, hey, I want to make some proof about the state there. You would go to the next slot, you would try to use it, and it would be gone. So instead we want to provide like some amount of history. And the way that the CIP implements this is with the ring buffer. If you're not familiar, just like imagine there's just a fixed amount of these slots here. That's what this data structure is supposed to, or this picture represents is the data structure. The idea is there's, say, about a day of roots that are in the storage of this precompile. And what that means is that rather than have to like be very precise about like when the root is on chain and when you try to prove something against it, you have like some buffer room, say a day. This also is nice because it bounds the state growth. An earlier iteration of this protocol, or this EIP rather, was basically going to like just write them all forever. And it wasn't going to be the end of the world, but it does have this like unbounded state growth, and generally we want to avoid that. So if we move to this world with this ring buffer in, say, a day of slots, a day of roots, then we have this problem with missed slots. What this means is that you could have the chain going, and again, if there's like reorgs or something, which we've seen are increasing, as if you saw the last talk. So these things happen, and they're out there. And what that means is that basically, from the chain's perspective, there was like, a block should have been there, but it wasn't. And this is a problem actually for this kind of design. So what I tried to communicate here is that you could imagine like everything is full. Let's say we like have written a day of history of these roots, and then we like are coming back around, and then this slot was missed. What would happen is that basically you would miss this entry here into the ring buffer, meaning it would basically be like the prior day's entry. And that's a problem because if you want to say, okay, if I have like the timestamp of this thing and that sort of maps into this slot or this index of this ring buffer, you would get yesterday's entry, and then you would be able to do bad things, meaning prove, for some time, you would have basically making proofs about old state, which we don't want to do. So the solution we came up with was basically to have two ring buffers, basically store the timestamp along with the root, and then you just check. If I claim that I want the root at this timestamp, make sure it's the one that was written last, and if it is, return the root. If not, just abort. This was like an excerpt from the EIP, which is what I just said. If you're curious, you can look. But basically, the idea is you have, well, there's more in the EIP, so I just, that's where all the details are, honestly. But essentially, the idea is you get the timestamp from the call data, do some sanity checks on like the format of it. The way one way to make these ring buffers is you just use like a modulus operation, so modulo arithmetic on the timestamp, modulo the size of the buffer that you want. That's used as an index into the first ring buffer. To get the timestamp, you can say, if this doesn't match, then just return like a garbage root, basically 0. And otherwise, get it from the other ring buffer and return it to the caller. So that's a high-level overview of the EIP. Yeah, so that's pretty cool. And now I'll talk some about these applications that I was alluding to. Perhaps more interesting unless you're like one of these core devs who are really into like the minutia of this stuff. So some things you could do. You could imagine this touching anything in Ethereum that needs access to like the validator state. So like things like staking pools, Lido, Rocket Pool, perhaps even Kiln, restaking like EigenLayer, and also, again, this is one where I'm trying to brainstorm some more things, but I think essentially even different like maybe management techniques would like use things like this. Anything that's going to like try and use the consistent state is essentially touching this beacon root somehow, and with this EIP, suddenly all of their like the trust model for all of them is like immediately improved because there's suddenly no reliance on this oracle. So just to like call out some specifics, I mentioned staking pools. So one thing you could do is look at validator lifecycles. So like just very simply, does this validator exist? Like has it deposited? You can imagine I'm like trying to join some pool, and maybe I'm like griefing the pool somehow by just claiming, hey, I'm a validator, and like here's my pub key, but it's actually not even in the state yet. Something like that. You can look at validator performance. So like the idea here is like, if you look at the history over time, we essentially record the performance of validators in terms of like the rewards or penalties they get. You could imagine like, compiling this down into essentially like a report card almost of like how good the validator is, and then this gives you some quality of like the operator that could be then used to like essentially place them into some kind of like risk bucket if you're making a liquid staking pool. And yeah, I did toss in a note. If you're doing something like this, you'd probably want a zero knowledge proof to like compress all of this computation. But it's something where you'd still want this root, and the CIP still would apply. Another bucket is like restaking. So again, if you've been around this week, you've probably heard of this thing called eigenlayer. The idea is to take the ETH locked on this consensus layer and like reuse it somewhere else. There's like some like very high level questions that eigenlayer today will ask, and again, they use an oracle to answer them, which is, for example, is a validator even like registered correctly? The way things like eigenlayer work is that they point to like a series of smart contracts into the EL, and there's like some data in the consensus layer, the withdrawal credentials that I think Mike mentioned. And if those are like not correct, then like you can't trust the validator to validate your application. Another one, again, very simply, like is the validator slashed? You could get to a case where you have a slashing on the consensus layer that basically then means your application is like no longer secured. But the way these things are designed is you actually wouldn't know. And so this would be something that any sort of restaking application would like really care about. Yeah, these get a little bit more speculative, kind of like I was suggesting, but I think even for like MEV management, so like one that's like fairly concrete, there's this notion of like registering your validator when you use MapBoost. If you're running a validator in this room, you've probably heard of MapBoost, and you probably are running it. And one thing you could do in pools is basically try to like rug the pool by changing this registration at the last moment. And there's like not any really way to get around this, at least with the current constructions, because there's no way to like verify this behavior. One thing I'm trying to do is move towards a world where these registrations do end up on chain so that you can then start to say, okay, well, maybe your operator in the pool is actually bonded, and you could like imagine fraud proofs against this type of attack. So again, just improving trust assumptions all over the place. There's something here. I'll just say this is like, well, so what I said here is like iterating towards an ePBS world. There's this whole like research topic of this thing called PEP-C. The way to think about it is rather than have like the auction of MapBoost in like one particular fixed format, you could imagine this being programmable. Some would say that like this is kind of what eigenlayer is driving towards. They're like very complementary ideas. And either way, you could imagine like having access to the consensus state helps you start to build these tools even today. For example, in ePBS designs, we think we're going to like likely have builders bonded on chain, and you could like prove that fact very much like you could if a validator is slashed or not. Yeah, I'll just leave this here. If this is like stoking any ideas, let's chat afterwards. And I think that was it. Otherwise, yeah, I mean, part of the EIP is that like there's like access now to this thing in like a trustless way, and like I'd really rather just be surprised with like some new stake pool idea you come up with, or any of the other things. There's like probably some overlap with like light clients. I was trying this morning to think of like a cool way that it like maybe improves bridges. All of them, I was like, well, no, you could probably do that on the EL already, or it didn't really make sense. But that being said, if you think of something afterward, I'll actually drop my Twitter handle way over here at the beginning. We'll just loop back. DMs are open. Let's chat. Any questions?
Yeah, I want to ask, like, I know you can't like store historical sort of consensus roots right now, but is there a way of maybe doing that? Like, if you use like just store all the roots in like a mountain range or like some other mechanism apart from a ring buffer, like, is there a way of like maybe providing historical consensus state as well?
Well, I mean, you could prove any of the consensus state that you want, right? So I guess how do you mean history?
Like store all the block headers or store all the roots in the past in some like data structure and then provided proof that it exists within that.
Right. So maybe what you're asking about, there are data structures on the consensus layer that commit to like all historical states and all historical blocks.
Oh, yeah.
So that's actually probably worth pointing out that like once you have this one root from 4788, you can basically prove like anything that's ever happened.
Oh, yeah.
Which is really cool.
Nice.
Yeah.
You have a question?
Hi. So I had a question about the choice of design, like how this fits into the EVM and sort of how you landed on a precompile. I know this is a similar mechanism with the execution layer, like block hash as an opcode, that has a similar, like logically circular buffer where it's like you're only able to go 255 behind. And then the second sort of follow-up question is why sort of put the state into the precompile contract itself instead of just treating it like a similar sort of like the execution layer, like magic value that it just holds on to an external storage.
Yeah, this is the point I was making about stateless clients. It's like much cleaner just to not like really like there was even another EIP to get rid of the block hash thing and do something very much like this. If we do want to get to a world where we're say like with vertical tries where like everything is under this like one root, then you can start to make proofs about like everything very seamlessly. Like even if we were to like, I'm actually not sure how they're thinking about this, but if they don't change the block hash the way it works, then you'll like be able to make vertical proofs about whatever, and then also you'll still need to like have this look aside thing. Yeah. So yeah, it's just like kind of an inelegance of like the sort of existing design, and this is a way to improve it. And then again, it will facilitate making proofs about the state if we move to paradigms like vertical tries. Yeah, does that make sense?
Yeah. One small follow-up question, I guess. In devising these EIPs, do you consider much like the effect that like hard forks have on layer 2s or other things that are somewhat EVM based, and like was that influencing the choice to use a precompile to like not introduce an opcode, or is that lower priority?
Yeah, I mean, this is actually a really good question. Like you could imagine mapping this to layer 2 and like sort of. Actually, I'm not even really sure what that would mean. Like, you know, so there is actually like optimism, for example, wants the same architecture of having there's like a consensus node, an execution node. But I don't even think they really have a notion of like consensus block in the same way. So I'm not even really sure what that would mean. And yeah, I guess the answer to your question is like no one's really been focused on that. But we probably should have been a little bit more. Yeah, like I know it's something we generally think about within these like core dev circles around like L2 compatibility and like how they use it. Yeah, it's a good point.
Someone else?
This is not super heavily linked like to this subject. I might be a bit off topic, but I'm impressed we're at this level of connection, you know, although I can't access from the EVM to something simple like the transaction hash. I don't know, do you know why? Or
the question is why can't we get transaction hashes in the EVM?
Yeah, and seeing your talk, it makes even less sense to me than before, than this that this simple feature isn't possible, or maybe it is, and I just don't know,
Yeah. So already today, even before this, this block hash opcode that the other guy mentioned, like from there you can then get to like you could prove that this block header was like the preimage of this block hash. The block headers commit to all the transactions. And the kind of downside there is that one thing is the proof would be much bigger because there's just different data structure that just needs a lot more stuff to actually like write the proof. So that's like not great, and they're like generally people find them unwieldy to work with. This like Merkle Patricia trie, if you've heard of this. So you could do this, and I mean, someone correct me if I'm wrong, but almost certainly, yeah, you would go from the transaction trie route, and you could make a proof down to some transaction hash. So you can do that today. And then also too, like we don't have the transaction hashes on the CL, so this actually doesn't touch this. But you can already do your thing today.
Okay. Thanks.
Anybody have a question? Thanks, Alex.